Image preprocessing for deep learning with a real Sentinel-2 Level-2A data. Welcome to new lecture in Advanced Geospatial AI, Deep Learning for Satellite Imagery Analysis. I am Dr. Azar Rasool, and today we are digging into image preprocessing for deep learning using real Sentinel-2 Level-2A data from GE. We will preprocess a satellite image patch from a 1 by 1 kilometer region in Brazil, preparing it for tasks like land cover classification, for example, forest and urban. By the end, you will resize, normalize, and augment real Sentinel-2 patches in Colab, ready for a CNN like ResNet 18. Why preprocess satellite imagery? Sentinel-2 data with its multispectral bands, RGB NIR, etc., requires preprocessing to be compatible with the deep learning models. Unlike the spectral index, NDVI and EVI, or tabular data, satellite imagery has spatial dimensions and high dynamic ranges. Preprocessing is critical to resize images. CNNs require fixed input size, for example, 32 by 32 or 224 by 224. But Sentinel-2 imagery vary in resolution and extent. Second, normalized pixel values. Scale reflectance values, for example, from 0 to 10,000 to 0 to 1 for stable training. Number 3, augment data. Apply transformations like rotation or brightness adjustments to increase dataset diversity, preventing overfitting in small geospatial datasets like our Brazil land covering example. Image preprocessing techniques. Here are 3 preprocessing techniques for Sentinel-2 imagery. First, resizing. Adjust image patches to be a uniform size, for example, 32 by 32 pixels, to match CNN input requirements using libraries like OpenCV. Second, normalization. Scale Sentinel-2 reflectance values to 0 to 1, typically by dividing by 10,000 to stabilize gradient descent in CNNs. Third, augmentation. Apply transformations like rotation, flipping, or brightness adjustments to enhance model robustness, especially for geospatial tasks like classifying forests against urban areas. We will use Python with a Google Earth engine for data retrieval, OpenCV for resizing, NumPy for normalization, and albumentations for augmentation, all in Google Colab. The demo will process a real Sentinel-2 Level-2A patch from a 1 by 1 kilometer region in Fijo, Brazil. We will ensure reproducibility with a random set control. Coding demo reprocessing a real Sentinel-2 image. Let's get hands on Google Colab to preprocess a real Sentinel-2 image patch from GE. We will retrieve a 1 by 1 kilometer image, extract a 32 by 32 patch, resize it if needed, normalize it, and apply augmentation. Open a Jupyter notebook, from the course resources and follow along. Install required libraries. OpenCV Python, NumPy, augmentations, Earth Engine API, and GEMAP. This comment outline installs the libraries we need. OpenCV for resizing images, NumPy for array operations, albumentations for data augmentation, and GEMAP for accessing GEE. In Colab, these are often pre-installed, but you can uncomment this if you are running locally. These tools are our foundation for preprocessing real Sentinel-2 imagery. Then import libraries. Here we import our libraries. We have got CV2 for resizing, NumPy for handling arrays, augmentations for augmenting our images, EEE and GEE map for GEE data, random and torch for reproducibility. These are the same tools we used in lecture 4, ensuring we are ready to work with the real Sentinel imagery. Next, set random seed for reproducibility. To make our results consistent, we set a random seed of 42 for Python's random, NumPy, and PyTorch. This ensures that any random operations, like data augmentation, give the same output every time we run the code. Reproducibility is critical in geospatial AI. Then authenticate and initialize GE. Now we connect to GE using our project ID. The try expect block checks if we are authenticated. If not, it prompts to run ee.authenticate, which opens a browser window in Colab to get a token. This step is crucial to access real Sentinel-2 data. Once authenticated, we are ready to pull satellite imagery. Then define region of interest, 1 by 1 kilometer in Fiji, Brazil. Here we define a 1 by 1 kilometer region of interest in Fiji, Brazil using coordinates that cover a mix of forest and urban areas. This small region, about 100 by 100 pixels at Sentinel-2's 10-meter resolution, is perfect for extracting a patch for our CNN. The coordinates ensure we are focusing on a specific area for consistent data retrieval. Next, we tried a Cloud3 Sentinel-2 Level-2A atmospherically corrected data from June 2023. We filtered for our region of interest, a 1-month date range, and less than 10% cloud cover to get a clear image. The dot sort ensures we always pick the earliest image in that period, making our data consistent across runs. Check if image exists. We added a quick check to make sure we got an image. If no image matches our filters, say due to much cloud cover, This raises an error to let us know. That's a simple but important step to avoid processing empty data, ensuring our pipeline is robust. Then select RGB plus NIR bands. We select our Sentinel-2 bands, red, green, blue, and near infrared, or B4, B3, B2, and B8. These bands are ideal for land cover tasks because they capture both visible colors and vegetation signals. This gives us a rich multispectral patch for our CNN. Export to NumPy array and extract a single patch. Now we convert the image to a NumPy array using GEMAP and transpose it from high width channels HWC to channels high width CHW, which is the format deep learning models like PyTorch expect. We extract a 32 by 32 pixel patch from the top left corner, covering a 320 by 320 meter area. Now we start with the step one of reprocessing image, resize to 32 by 32. Step one is resizing. We use OpenCV's CV2.resize to ensure our patch is 32 by 32 pixels, which matches many CNN input requirements. Since our patch is already 32 by 32, this step doesn't change the size, but we include it for flexibility. If we had a larger patch, this would scale it down smoothly using linear interpolation. The output confirms the resized shape is still for channels 32 by 32 pixels. Step 2 is normalization. Sentinel-2 Level-2A data has reflectance values from 0 to 10,000, which is too large for neural networks. We divide by 10,000 to scale them to 0 to 1, making training more stable. Look at the normalized sample for the top left pixel. The value is higher, typical for vegetation areas in Brazil, aligning with the forest data. Step 3 is augmentation, where we make our data more diverse to prevent overfitting. We use augmentations to create a pipeline with the three transformations, random rotation up to 90 degrees, a 50% chance of horizontal flipping, and brightness or contrast adjustments limited to 20% to keep changes subtle. These transformations mimic real-world variations like different lighting or angles, making our CNN more robust for tasks like land cover classification. Then apply augmentation with a seeded randomness. Here we apply the augmentation pipeline. We set the random seed again to ensure the transformations are reproducible. Albumentations expects the image in height width channels format, so we transpose the normalized patch, apply the augmentations, and transpose back to channels height and width for PyTorch. This ensures our augmented patch is ready for a CNN. Debug. To make sure our augmentations worked correctly, we check the mean and max values of the augmented patch. Let's run the code, starting with the change runtime type, selecting GPU, save, and run the code. It's just executed. The script runs correctly. The output is original patch shape for 32 by 32 for channels with 32 by 32. Augment patch mean 0.0064, maximum 0.41. Resized patch shape, the same like original one. Normalized patch sample, first band 0.015, second band, third band, and near band 0.31. Augmented patch sample, first band 0.13, second band 0.14, and so on. Today we learn how to preprocess real Sentinel-2 imagery with the resizing, normalization, and augmentation, preparing it for deep learning models. You process a real image patch in Colab using GEE. Action items. Run the demo notebook to preprocess a real Sentinel-2 patch. Complete the assignment, apply augmentation to another Sentinel-2 Level-2A patch from GE, and report changes in pixel values in Q&A. Take the quiz to reinforce your understanding. Let's keep advancing your geospatial AI skills.